These questions are framed exactly in line with the patterns of previous year's papers, focusing on critical phenomena like Maxwell's distributions, critical constants, and intermolecular forces. Part A, Conceptual and Derivation-Based Questions. Question 1, 10 marks. Account for the fact that the van der Waals constant A is a measure of intermolecular forces, while B is a measure of molecular size. Derive the units for both constants. B. Explain why hydrogen and helium show positive deviations from ideal behavior, Z greater than 1, even at very low pressures. Answer. Physical significance and units. The van der Waals equation for 1 mole of a real gas is given by. Significance of a ideal gas theory assumes no intermolecular attractions. In real gases, molecules attract each other, reducing the force and frequency of collisions with the container wall. The term, frac A, V squared, is the cohesive pressure correction. Therefore, A directly quantifies the strength of attractive intermolecular forces. Significance of B. Ideal gas theory assumes gas molecules are point masses with negligible volume. In real gases, molecules have finite sizes, making a portion of the volume unavailable for free movement. The term B represents the excluded volume or co-volume, which is approximately 4 times the actual volume of the gas molecules, B equals 4 NaV. Derivation of units. For A, since frac A, V squared, has the dimensions of pressure, P. For B, since V, B, involves subtracting volumes. B. Behavior of H_2 and He. For hydrogen and helium, the molecular masses are extremely small, meaning their mutual attractive forces, text, van der Waals forces, are exceptionally weak. Consequently, their constant A is negligibly small, approx O. Applying this condition to the van der Waals equation. Dividing both sides by RT. Since P, B, R, and T are positive, the compressibility factor Z greater than 1 at all pressures. The repulsive forces dominated by the finite size, B, entirely overtake any negligible attraction. Question 2, 15 marks, state the principle of corresponding states. Using the van der Waals equation, derive the reduced equation of state and show that it is independent of the nature of the gas. Answer. Principle of corresponding states. If 2 or more gases have the same reduced pressure and reduced temperature, they will occupy the same reduced volume. Essentially, it implies that all real gases behave similarly when scaled relative to their respective critical properties. Derivation. Let the reduced parameters be defined as the ratio of the actual property to its critical property. From the derivation of critical constants using the van der Waals equation, we know. Substituting P, V, and T into the van der Waals equation for 1 mole. Substitute the values of P_C, V_C, and T_C. Factoring out, frac A, 27B squared, from the first bracket and B from the second. Cancelling the common term, frac A, 27B, from both sides yields the reduced equation of state. Conclusion. This equation contains absolutely no gas-specific constants, A or B. Hence, it is a universal equation applicable to all real gases, validating the principle of corresponding states. Part B, Numerical and Analytical Questions. Question 3, 10 marks. Calculate the root mean square velocity, U_RMS, average velocity, U_AVG, and most probable velocity, U_MP, of CO_2 gas molecules at 27 carat, circ, text, C. Answer. 1. Given data, gas, carbon dioxide, CO_2, implies molar mass, M, equals 44, text, gram per mole, equals 44, times 10 carat, minus 3, text, kilogram, CDOT mo, carat, minus 1. Temperature, T, equals 27 carat, circ, text, C, equals 27 plus 273.15 equals 300.15, text, K. Universal gas constant, R, equals 8.314, text, J, CDOT carat, minus 1, CDOT, text, mo, carat, minus 1. 2. Formulae and calculations. Most probable velocity, U_MP. Average velocity, U_AVG. Root mean square velocity, U_RMS. Verification of ratio check. Question 4, 15 marks. The critical constants for a certain real gas are P_C equals 45.6, text, ATM, and T_C equals 190.6, text, K. Calculate the van der Waals constants A and B for this gas, and estimate its critical molar volume, V_C. R equals 0.0821, text, L, CDOT ATM, CDOT K, carat, minus 1, CDOT, text, mo, carat, minus 1. Answer. 1. Identification of formulae from van der Waals expression for critical constants. 2. Calculation of B. 3. Calculation of A using the computed value of B. 4. Calculation of critical molar volume, V_C. Alternative cross-check via V_C equals frac 3RT_C, 8P_C. Question 5, 10 marks. Using Maxwell's distribution of molecular speeds, explain visually and mathematically how an increase in temperature affects the fraction of molecules possessing the most probable speed. The shift in the overall distribution curve. Answer. Maxwell's distribution function is expressed as effect on the peak height, fraction of molecules with U_MP. The fraction of molecules at the most probable speed is inversely proportional to SQRT, T. As temperature increases, T_2 greater than T_1, the term left, frac m, 2, pi RT, right, caret 3/2, decreases. Consequently, the peak of the curve flattens out, meaning the fraction of molecules possessing the most probable speed decreases. Shift of the curve, because U_MP equals SQRT, frac 2RT, m, a higher temperature pushes the maximum point of the curve toward higher velocities, to the right. To maintain the total area under the curve constant, which represents the total number of molecules, int, frac dn_u, n, equals 1, the distribution broadens out and shifts downward and to the right.